Welcome to lesson 1. So this particular lesson, it's a little long, but the entire thing is going to be Stat 201 review. So we're going to kind of review the highlights of Stat 201. It might have been last term, it might have been longer since you last took it. So one of the key things in stats is remembering what the goal of doing stats is. And typically it's going to be answering some question about some greater population, and we're going to use some sort of sampling method and either study design or experimental design to help answer that question. So it's really, really important to be able to understand the relationship between the sample and the population and be able to use that in order to make better predictions and statements about that population. So when obtaining data, one of the first things we want to look at is where do our data come from? We don't want to just pick the most convenient. We really want to be careful about how we select our samples. So uses random chance. What this means is we use some form of random sampling. This could be simple random sampling. This could be stratified random sampling. So like when it's important to make sure that you have certain groups covered. So suppose I want to look at high school students, I might want to take a random sample of students from each grade. That way I ensure that I have representation of each grade. Or systematic, and that makes more sense when you have things in a certain order, like an assembly line. Maybe you want to take every 10th part off of a conveyor belt and check it, something like that. People can be a little harder to use systematic sampling with because they rarely tend to walk by in a single file line. I'm not saying it never happens, but it's a little harder. So then looking at our study design, so now that we have our sample, experiments, they are a happy place for us statisticians because they ideally use random assignments. So you usually have like a treatment and control or different treatments, and you randomly assign which individuals go into which treatment group. Replication, this is when you have more than one individual per treatment. I mean, if you think about it, if you had a treatment group with one person in it and another treatment group with one person, it's really hard to say that those results would carry to the general population because it's only one, right? Ideally, you're going to have replication. You're going to have many people getting treatment 1 and many people getting treatment 2. And often we do like to control for things. We want to make sure that there's some sort of baseline that we're comparing to a lot of the time. So general experiment themes that we're using, at least from 201, so that completely randomized design, that's when you have 2 or more treatments and you just randomly assign, if you have 2 treatments, you randomly assign half to treatment 1 and the other half to treatment 2. Randomized block designs, so this means that there's some sort of third variable that's important to control for, but it's not necessarily what you're interested in. So you might want to go ahead and, like if you had 2 types of grass and you want to test, you really are interested in the effect of the fertilizer. You have 2 fertilizers. You might say, okay, well, half of grass 1 is going to have fertilizer 1. Half of grass 1 is going to have fertilizer 2. And then do that with the other grass as well. While we're not really interested in the particular impact of the grass itself, you want to make sure that you're not assigning all the fertilizer to one grass and all the other fertilizer to the other type of grass. Then you can't really separate, the effect of the fertilizer from the type of grass. And then match pairs. So that's a special kind of block design. A lot of times this might be like pre and post, before and after. If you have multiple measurements on the same individual, I was part of a study where they went ahead and they put ink on my right arm and ink on my left arm. I don't remember what they were measuring, but that would have been an example of a matched pair design, that my right arm goes with my left arm, and they took a difference between what they observed there. So types of variables, as far as we're concerned, pretty much anytime there are two main types of variables we're really interested in looking at. So the first there, it's going to be categorical. So this is when, so you have your individuals in your sample. The information that you're collecting on those individuals is something, it's qualitative. There, it has categories. Maybe you record it, it's yes, no. You might record eye color, brown, blue, green, and so on. Those are usually not number values. They wouldn't make sense to take an average of. And typically they're categories, days of the week, political party, that kind of thing. So you can describe it as a category, as categories. The other is quantitative. So this is going to be something, it's going to be a numeric value, so it's going to be a number. And not only is it going to be a number, it's going to be a number that makes sense to average, right? So weird exception here is zip codes. While they're numbers, they really correspond to categories, to actual places. So it would be categorical. They're numeric, but they don't make any sense to average. So in this sense, like if you had heights or weights or distances or pretty much any sort of very quantitative feature there, you have yourself a quantitative variable. So looking here, once we have our variables and we know that it's quantitative or categorical, then we can talk about what type of plots we would use. So for categorical, we are interested in summarizing with proportions. So typically P. If you have more than one group, like P1 and P2. If you have a sample, you would use P hat. But remember, if there's a hat, it means it's related to your sample. You can use pie charts or bar charts. So bar charts are really the ones that we're going to stick with in this class. But pie charts, they're really, really popular out there. They're that round with wedges, and the wedges kind of correspond like, hey, this percent of this goes to this category, that sort of thing. Bar charts, statisticians tend to like bar charts a little bit better. Quantitative. So if you have a quantitative variable, there are so many different options for summary statistics. So like you can look at means, standard deviations, medians, that interquartile range or IQR, you could use that. You could use range. There are a lot of values you could use. And the three kind of plots that we are going to use in 202, pretty much they're going to be histograms, stem plots, and box plots. So those will be the three key kinds. Know that there's a lot out there, but those are the three key ones. So populations versus samples. So it's really important to know what group or that we're actually talking about. So I like to think P for population, P for parameter, population parameter. These are talking about features about this overall bigger population. This is usually the larger group that you want to make a statement about. This could be all Oregon State students, or all Oregonians, or all U.S. voters, or all adults in the world. I don't know, that's a pretty big population. But it's the idea that it's the entire collection, so all of the individuals in the group that you want to make a statement about. Usually hard to access all of them. So when you're dealing with population parameters, we tend to use Greek letters most of the time. So we have the Greek letter mu. Sorry, my mic is like falling on me right now. So this is a Greek letter mu. We have that Greek letter sigma and the letter P, which might seem a little weird. However, it kind of comes down to old school textbooks used to use the Greek letter pi, and that got really confusing really fast. So this is us trying to not be confusing. So population parameters, this is the whole group. Now if you take a subset from that whole group, now you have yourself a sample. And just a note, we usually don't know the values of the parameters. We usually want to make a statement about them, but don't actually know them. So sample statistics. So sample statistic. So this is going to be a feature that you take a smaller group from that population. So you sample a smaller group from the population, you have yourself a sample. And these don't get Greek letters for the most part. You're going to get X bar for the mean, the letter S for the standard deviations of the sample standard deviation, and P hat for the sample proportion. In general, anytime there's a hat, know it's an estimate that came from a sample. Anytime. And so these are known. This means you collected an actual sample and you calculated these actual values. So you can know these. But know that from sample to sample, these can vary. So if I take a sample of 50 observations and calculate a mean from those 50 observations, that mean may not be exactly the same if I were to take another sample of 50 and take that sample mean. It can vary, right? Because not all observations are identical in the population. So inference, which is really the main goal of statistics. You want to make a statement about the population, ideally not actually having to collect the entire population information. Ideally, if you do it correctly, you can take sample information and make a statement about the population. So you start off here. You maybe want to know the average weight of all African elephants. Good luck taking a random sample of any animal. Like animals, they're really, really hard to do, especially if they're in the wild. So I have this whole population, so let's pretend that's all of the African elephants in the world. I'm taking a random sample of them, so I'm not taking as many as are in the population. I have a smaller group, and I'm going to calculate the average weight of those elephants. And now I'm going to take this X bar sample mean value, and I'm going to make a statement about what I believe the mean of the population actually is or isn't. So that is our goal. That's almost always our goal. And the idea here is if I don't take this random sample, I don't get to make the connection. I don't get to say, hey, this is what I saw in my sample. I can say this about the population. You don't get to do that step. It's very problematic. So as I hinted probably a couple of slides ago, is from sample to sample can vary. So if this is my population and I take a random sample of, looks like 7 elephants, so I have a sample of 7, I can get a sample mean for those 7. But then suppose I take another sample and I get another sample mean and another sample and another sample mean and so on and so on. Every time I take a sample, the sample means a little bit different, right? Sometimes it might be the same or really close, but sometimes it might fluctuate. Totally depends on what elephants are my sample. So the idea here is, how can we account for this variability? Like we know that it varies from sample to sample. So we need to factor this into our statements. Like when we say, hey, this is the sample mean, we can say this about the population. We have to factor in how much it varies into our statements. So here, the sampling distribution of X bar. So this is the idea. If I took every single sample of 50 that I possibly could from the population, so I have however many samples of 50, and then I calculate a sample mean for all of those samples, I have a ton of sample means now. And if I put those into a distribution, those are a distribution of X bars. So all the unique sample means I could possibly get are up in here. If my sample size is big enough, and this is important, so if it's sufficiently large, so big enough, then I know that the sampling distribution of X bar is going to be roughly normal, so it's going to be this lovely bell shape with a mean of mu, which is nice, it really doesn't change up, and a standard deviation of sigma over the square root of n. And the idea is the bigger your sample size is, the smaller this gets. So this is that sigma of x bar. Because you're dividing by the square root of n. So if n gets bigger and bigger, sigma over the square root of n gets smaller and smaller. And one way to think about it is if I were taking samples of 20 students and looking at midterm scores, why not? If I took a sample of 20 students and I calculated the average score, and then I take another sample of 20 and calculate their average score, the average score for those 20 students would vary somewhat from each sample of 20 that I took. If I had instead said, you know what, I'm going to take a sample of 100, and then I'll take another sample of 100, and another sample of 100, from sample to sample, the average is going to vary a lot less with really big sample sizes. Basically, it's going to be a lot more consistent. It's going to be a lot closer to that average of the population more often. So sampling distributions is statistics. So sample statistics, they serve as our point estimate. What that means is if I want to know the average of a population, the place I'm going to start, I'm going to take a sample, calculate the average, and that's going to be my starting point. That's my point estimate. That's where I'm going to start. So if I want to find out the population height of all OSU students, and I take a sample of 50 OSU students, the average of those 50 OSU students, that's going to be my starting place. That's going to be where I start. Sample statistics are random variables, so that means every time I take a sample of 50, that sample mean can vary. So from sample to sample, that sample mean can be different. It follows a probability distribution, so like we said, when we know that n is big enough, and we do have some definitions of what big enough would be. Usually, if you're dealing with means, 30 is going to be big enough. It's a little bit different if you're looking at proportions. But we knew, hey, if it's big enough, that distribution is roughly normal, so it's that nice bell shape. We know where it's centered roughly, and we know its spread. So the sampling distribution of the statistic, it's going to be the probability distribution that specifies probabilities for all the possible values that statistic can take. So I want to know how weird is it if I took a sample of 50 OSU students and had an average height of 68 inches. What is the probability that I would have seen taken a sample of 50 and gotten 68 inches or taller? I can find that probability now. And it's absolutely helpful in figuring out that variability for that sample statistic. So here's an example. It's a great place to pause and give this a try. I'll go ahead and pause a moment after I read it. So suppose we have a sample of 36. I'm not sure 36 what, and we randomly selected these 36 from a population that has a mean of 15 and a standard deviation of 18. So based on what we know, what is the sampling distribution of the sample mean? So I'll give y'all a second. Okay, so here you might notice they all have mean 15. Remember, so mean of that sampling distribution of x bar is just going to be equal to the mean of the population. We know that already, it's 15. The standard deviation is the trickier part. So it's that sigma of x bar, and that sigma of x, or just sigma. That's fine if you don't put the x there. I find it helpful. Over the square root of n. So sigma of my population, that's 18. Note that we often aren't actually lucky enough to know what sigma is in real life. So we happen to here. And then 36, which is so nice, it's a square. So we end up with 18 over 6, which is 3. So looking here, standard deviation 3. B is going to be our choice here. So now we have another example. So we're looking at the average time spent waiting at a doctor's office being 15 minutes with a standard deviation of 18 minutes. Relatively, that's kind of a big standard deviation. So here, this is mean because it's saying, hey, this is the average time waiting at this doctor's office. This is implying sigma right here. What is the probability the average wait time from a sample of 36 patients would exceed 20 minutes? So here, this is my n. So 36, it's higher than 30. We know that that central limit theorem is going to kick in, and we can say, okay, well, that distribution of x bar, it's going to be roughly normally distributed with a mean of mu and a standard deviation of sigma over root n, which we can find. So here, I'm going to say x bar, it follows a normal distribution. Mu is 15 minutes. And then sigma over root n, so that's going to be, what, 18 minutes divided by the square root of 36. So it's going to be, well, I could just put it in here, 3. So that's if I had this distribution here. It's centered at 15, and the tick marks are 3 away. You can write all of them if you want. 20 minutes. So 20 is here. Exceeding means higher than. So 20 minutes or higher. We want to know the probability of that right there, that wedge. So we can't use that empirical rule because it's not an exact number like of tick marks away. So we can find a z statistic, or a z score. So z is equal to x bar that we actually observed minus the mean over sigma over root n. So I have everything I need to plug this in. So we want to know 20 minutes. That's what I'm going to plug in for x bar. So 20 minus 15 over, this is that 18 over the square root of 36, that's 3. So I end up getting 5 over 3. It's about 1.67. So this is my z statistic. So it's positive 1.67. What this means is I am 1.67 tick marks above average. So it being positive means 20 is above the average. 1.67 means it's 1.67 tick marks or standard deviations above. So now here's where we need a z-table or a calculator if you know how to use it. Oops. So 1.67, I would break into 1.6. So I would use this row, and 0.07. So use this column, and where it lines up. So I'm going to erase some stuff here. So if I have 1.67, it's saying that this blue area is 0.9525. If I want the area here, this exceeds, I need to use some subtraction. So this is actually going to be 1 minus, because the whole area under this curve is 1. So 1 minus this 9525. So 0.0475. So what this means is if the average wait time is 15 minutes with a standard deviation of 18 minutes, then anytime I take a random sample of 36, the probability that I am going to get an average wait time for those 36 of 20 minutes or longer, that only happens about 4.75% of the time. So not too often, which is good. I would not really enjoy waiting over 20 minutes every time. Okay, so here's another question, and by all means, you are more than welcome to press the pause button here. I strongly encourage it. Give this a try before watching me work it out, because it's not nearly as helpful to watch me do it as it is to attempt it. So we have this probably really ancient data set where we asked a bunch of OSU students, how many minutes on average do you work out every day? And we ended up seeing an average of 20 minutes and a standard deviation of 19 minutes. We'll say for the entire population, which would be kind of weird. So what is the probability that a sample mean from a sample size of 150 would exceed 30 minutes? So before I get all worked up here, so my mean is 28 minutes. And I like to keep my units here. My standard deviation for the population is 19 minutes. We have a sample size of 150. And we're interested about exceeding 30 minutes. So that's actually X bar, is 30 minutes. We are going to set this up exactly the way we did before. So one thing to note, so sigma of X bar, that's sigma over the square root of n, which is, off the top of my head, I cannot do this math, especially since there's a prime number involved. But it's going to be 19 divided by something bigger than 13, but I think it's smaller than 14. I could be off, but technically that's also minutes. So I want to know, hey, I know off the top of my head it's centered at 28 minutes, 30 minutes. I'm not sure how many standard deviations that is off the top of my head. But that's okay. We're going to calculate it using a z-score. And exceed. So I want higher than. So we're going to have to do that 1 minus bit again. So z is equal to x bar minus mu over sigma over root n. So I want 30. 30 is above the average, so right off the bat I know that my z-score is going to be positive. It should be anyway. Minus 28 divided by 19 divided by the square root of 150. 150 is a nice good big sample size there. So I'm going to do some magic math here. Absolutely throw this in a calculator and check it. This is not math I do in my head, so do not feel bad if you cannot do this in your head. I cannot either. So I want to know, if I want to know the probability that x bar is greater than or equal to 30, or, well, greater than 30, that's really the same here. It's the probability that z is going to be greater than or equal to 1.29. The idea is I don't have a normal table that I can find the probabilities for here, for the x bar, but I do have a normal table that I can use now that I have a z-score. So cue the z-table, which is probably going to sort of appear there. So 1.29, well, right here, 1.29. It's going to go into 1.2 and 0.09. The idea is if I add them back together, I get back to 1.29. So obviously this is a very doctored version of the table. It has just the part I want. Right here. So it's saying that this blue area is 9015. But be careful, we want exceeds, so we actually want the yellow area. So you're going to say, okay, well 1 minus 0.9015, it's going to be 0.0985. And this is where I kind of look at the class and go, check my math, my mental math. That's definitely where I make goofs. So this would be saying, hey, this happens about 9.85% of the time. I take a sample of 150 and I get an average daily exercise time of 30 minutes or higher. So there are a few different distributions we like to talk about. The first one is usually the one that we really want to make a statement about. It's also the one we usually know the least about. It's the population distribution. So it's the distribution of all the observations in that population. And it's really uncommon for us to actually have access to all the individuals. So like even if you could access everyone, the time and resources it takes to actually measure or survey every object or person in a population, it's a lot. So once I have a population distribution, the first step for us is we're going to take a sample. And that sample we can throw into like a histogram or a bar plot. And that is our sampled, which is a D right there, right? So it's our sampled distribution. And I'll mention in a second why I am emphasizing the sampled. So this is a distribution of a specific data set that is a sample. So this is us just plotting a specific data set. If I were to take another sample, I would have a different sampled distribution. And the idea now is if I were to repeatedly sample and just record like the sample mean and only plot the sample means, that's my sampling distribution. So sampled is the actual sample itself. Sampling is saying, hey, if I were to repeatedly take samples of the same size, take the sample mean from each one, so I have all the unique sample means from all the unique samples I could take of whatever size, that's my sampling distribution. Once again, that kind of, in order to actually access that, we would actually need access to the entire population. So it's one of those things where we kind of know, hey, we have this relationship here between these various ones, and we're going to count on, hopefully we have a good sample. So a little bit on the central limit theorem. It saves our butts in this class, although we will have a couple of non-parametric tests we use later on. So if we have a population of, let's say, all OSU student heights, and we know that those heights are normally distributed, so they follow a nice bell shape, we know what the mean is and whatnot, it really doesn't matter what our sample size is. This sampling distribution of X bar is going to be normally distributed no matter what sample size you use. We're really happy with any sample size if you know that the population is normal. However, then there's that non-normal population. So if you know, let's say the population is really skewed or there are some really extreme outliers, something like that, then you really have to be careful and make sure that we take a big enough sample size for that central limit theorem to kick in. And we need that sample size to be big enough. And general, so it is kind of funky to think about if you really get into it. We like a sample size of at least 30. But that's us saying 30 is really close to infinity. And I don't know about y'all, but if I were to look at my bank account and see 30, the reason I'd be crying isn't because it's close to infinity. I don't know. Just keep in mind, it is big enough to make this central limit theorem kick in most of the time. Just take with a grain of salt that maybe it's not super close to infinity, but it's big enough. So here's just some views here. So if I were to take a very skewed population and I take all unique samples of what here? So here's my population data. It's very, very skewed. It has a mean of 4 and a standard deviation of 3.78. If I go ahead and I take every single unique sample of 5, so all possible combinations, I could possibly take 5 individuals from this population, take the sample mean from all of those samples of 5. Here's my sampling distribution of X bar, which you can see it's a little skewed. It does not curve up at the end there. It's not nice and symmetric. Not yet. Not symmetric enough. When we increase our sample size, so now let's take every single unique sample of 30 and take the sample mean from all of those unique samples of 30. If you look here, oops. Obviously drawing on these graphs is not my strong suit. It does look pretty symmetric. It does look pretty bell-shaped. We're pretty happy with this. And if you just increase it, it looks normal, and not only does it look normal, it looks narrower, and we really like it. The more normal and the more narrow it gets, the happier we are, because the more precise our estimates and statements they can get. So why is it important? Well, for starters, it lets us know from sample to sample how much variability there is. If central limit theorem doesn't kick in, we really don't know. It makes it very, very difficult to move forward. So, really important for the critical values that we use making confidence intervals. So, when we do that X bar plus or minus either Z star or T star, it's really, really important to know that central limit theorem's kicked in before we can use that equation. The fact that we're using a T star or Z star is completely dependent on the central limit theorem kicking in. It is where we get our p-values from. So if our sampling distribution of X bar doesn't follow a normal distribution, we are really getting our p-values from the wrong place. And that can be really problematic really fast. I thought we had 3. Sorry about that. These assumptions. So, estimation versus hypothesis testing. So, it all comes out to what kind of question are you asking? So, think of estimation as open-ended, like what is the average height of all OSU students? And hypothesis testing is a yes or no question. Are all OSU students on average taller than 5 feet? I don't know. So for estimation, our goal is we want to estimate a specific characteristic. So typically if we're dealing with something quantitative, it'll be a mean. It depends. It could be the median. There are other tests that test other things, but those are definitely the most common when you're dealing with something quantitative. And so it includes a point estimate. So what we actually observed in the sample plus or minus some amount gives us our interval. And then hypothesis testing, we want to make a statement. So we want to test a claim and make a statement about the population parameter. So is the average body temperature of U.S. adults less than 98.6 degrees Fahrenheit? Well, that's like a yes or no statement. So we want to be able to test this claim and say, yeah, I believe it is, or no, we don't think it is. That kind of idea. So we're going to obtain a likelihood of truth, which is a funny way to put it. So based on, hey, if it really were 98.6, what we observed in this sample, is it weird if it is? Maybe we don't think it's 98.6, that kind of idea. So estimation, so confidence intervals. So estimation, you can always just think this is confidence intervals. You want to estimate it. Like what is? So your point estimate's your starting place. You're going to start trying to estimate the population mean by calculating your sample mean. Your sample mean's your starting place. It's your best guess. Given if you only have your sample data, your sample means the best place you have to start. So if you are looking for a population mean, mu, you're going to start off with a sample mean, x bar. If you want the population proportion, which is p hat, which is the sample proportion, that's going to be where you start. So your interval estimate, this is the confidence interval, so from smaller value to bigger value. It gives a range of values. And one way to think about this is so much more useful than if somebody were to say, hey, what is the average test score out of 100? And you took a sample of, 5 students and got an average of 78. Well, 78 as a guess by itself is right or wrong. And it's probably wrong a lot of the time. Versus if you gave a range of values, we think it's from 78 to 81. That's a way more likely to be correct statement. That's the idea here. So we get a range of values with some degree of uncertainty. So this margin of error, it's your point estimate plus or minus this margin of error. So maybe it's 78 plus or minus 3 points. That kind of idea. My margin of error would be 3. So they all are going to have the same general format in this class, where we have some point estimate, plus or minus. So your critical value, so this is either Z star if you're using Z methods, and there are conditions. If you meet, you can use Z star, or T star. So those are the only two that we've really gone into 201. And it's going to totally depend on whether or not you have access to population information about the standard deviation. Then times standard error. So this is saying, okay, well, if you're looking at mean sigma of x bar, if you don't know sigma, and so you're using the sample standard deviation to estimate, it's standard error of x bar. So just a few things to note. This point estimate, it's always going to be whatever we actually observed in the actual sample. And the critical value, that's my Z star, T star. My standard error. So typically it's either sigma divided by the square root of n, if you know sigma, or S over the square root of n if you don't know sigma, so you have to use the sample standard deviation. And as you can see, n is in here. If n is really big, it's going to make the standard error really small. And if n is really small, it's going to make your standard error really big. So it definitely is impacted a bit by your sample size. So looking here, we're just going to try to identify parts. And I swear that's half of stats is interpretation, being able to read a prompt and figure out what parts are what. So we have an ecologist. They're really, really interested in a particular river, the zinc concentration in this particular river. So they go ahead, they pick 36 locations on this river at random, and they go ahead and they measure the zinc concentration in those 36 spots. And they find that the average in those 36 spots is 26 grams per milliliter. And then, this is funny language, it is known that the zinc concentrations vary on average. This vary on average tells me this is a standard deviation. This is some of the weird language we use sometimes when we want to say standard deviation. So, this is sigma. Is 3 grams per milliliter. So the point estimate, if we want mu. We don't know it, but we want mu. Our point estimate is going to be the sample mean, x bar. So looking here, that's going to be that 2.6 grams per milliliter. So right here. Typically we like to throw in units, but for this problem it's not a huge deal. So if I want to figure out the average zinc concentration for this entire river and I have this sample data, my best place to start is going to be 2.6 grams per milliliter. It's better than a wild guess. So now constructing the confidence interval. So it's that x bar plus or minus z star times sigma over root n. So once again, this is only if I know sigma. Z and sigma go together. If I don't know sigma, I have a t star, which you have to use a t table for, times s over square root of n. So t and s go together, z and sigma go together. So when we know sigma, this is good. We know the sampling distribution of x bar, so the sampling distribution of the sample mean is normally distributed with a standard deviation of sigma over root n. And I can use these z-star critical values. So 1.96 for a 95% confidence interval, 1.645, and absolutely feel welcome to write these down. They're also given at the bottom of the t-table. It's handy. Are you expected to memorize them? No. I've used them enough that I probably won't forget them for a while, but we don't really expect people to memorize numbers here. So definitely something to consider. Why is this true? What theorem are we using? Hopefully this is familiar. Just a few slides ago. So conditions for using a confidence interval. So specifically, this one is for using Z methods or Z procedures. That's not a good T. Okay, so this wording is a little funky. The sample is obtained using a random mechanism. What this means is it's a random sample. So did I take a simple random sample? Did I take a stratified random sample? Systematic random sample? Then we're happy. We want to know the sample size is big enough that the central limit theorem is going to kick in. So in general, if our sample size is at least 30, it's good. If it's not at least 30, we're going to be a little wary. We're going to want to know, well, hey, what does the population look like? If we don't know that, we're going to try and look at the sample. And if the sample looks really nice and normal, we can say, hey, the population's probably nice and normal. If the sample's really skewed, the population's probably pretty skewed. So you want to be wary. If your sample's really skewed and your sample's really small, this is not good news. And then the last one, specific to the using Z methods, we know sigma. So Z methods, Z procedures. And then next we're going to get into using T procedures, which also I want to say in 201, it was either that, I want to say the second to last week, probably. Maybe third, depends. So we still have this ecologist who is obsessed with the zinc concentration in this river. And they want to know, hey, what is the average zinc concentration? Well, telling them 2.6, that's either right or wrong, and it's likely that it's not exactly correct, right? It's probably off by at least a little bit. So they want the 95% confidence interval for the mean zinc concentration. My first step is going to be writing out what I know. I know my sample size is 36. I know that my sample mean was 2.6 grams per milliliter. Sigma, so standard deviation of the population, that's that 0.3 grams per milliliter. Sigma of x bar, you don't have to calculate it here, but I like to. Sigma over root n, so that's 0.3 divided by the square root of 36. I want to say it's 0.05 grams per milliliter. And then Z star. So this is going to depend on, it's a 95% confidence interval. I know sigma, so Z star is appropriate to use, and it's going to be 1.96. And that just comes from that table that we had a slide or two ago. So now I want to know, okay, plug it in. So x bar plus or minus. So z star times sigma over the square root of n. And now I have everything I need to plug into this. So x bar was 2.6 plus or minus 1.96. This part right here, if I just plug in that, it's times 0.05. Feel free to plug in the 0.3 over square root of 36. That's okay too. I end up getting something like, plug this into a calculator. So 2.502 grams per milliliter to 2.698 grams per milliliter. And since it's interval notation, I'm going to put the parentheses at the end. So, oops, I cannot keep my mic up today. So the idea here is smaller number to bigger number. Smack in the middle is 2.6. If 2.6 isn't in your interval, something went wrong. So my 95% confidence interval for that mean zinc concentration for all locations on this river is 2.502 grams per milliliter to 2.698 grams per milliliter with a point estimate of 2.6 grams per milliliter. I do not have familiarity enough with zinc concentrations to explain what those units really mean, but maybe I believe at least one of y'all will. So TI-84, I have not seen an 88, I've seen an 89. If you wanted to run this on your calculator and you have an 84 or an 83, they both have this feature. You would go to this stat button, you would go to tests, and if you want a z interval, you just give it those values and plug it in and tell it, I want 0.95 for 95%. If you wanted a 90, you'd say 0.9 or 0.90. And then here's that interval. And yeah, pressing calculate, that's probably an important step. So the idea behind confidence intervals is kind of funky because 95% confidence, and people are saying, hey, wait, what's my confidence in? Our confidence is in the confidence interval making process. So that means 95% of the time that I make intervals this way with samples of 36, 95% of those intervals have the actual true population mean in it. So what we're doing is we're really hoping that our sample was one of those good samples that has the true mean in it. There's no way of really knowing. We absolutely could have one of those, bad samples that doesn't have the real mean in it, in the interval calculated. That would be a bummer. So the idea is all of these are unique samples of all the same size. And every once in a while, like this particular confidence interval, it missed. Like it was supposed to have this value here. That entire interval is above that value. So it doesn't have that true mean in it. So the idea is if I'm looking at the zinc concentration example, if I were to take 100 samples of 36, so random samples, and that's important, out of those, I would expect roughly, not exactly, not always, but about 95 of those samples. If I calculated the mean and went ahead and calculated a confidence interval, 95 of those confidence intervals, roughly, would have whatever that true mean zinc concentration of that river located in it. We are just hoping and praying that, the actual one sample we took is going to be one of those 95 or 95% that would contain it. So If y'all had me earlier for 201, I put out this template. I definitely recommend giving it a go. We aren't necessarily like you must put everything in this order, but I find it useful as kind of a checklist. So you should mention your confidence level. Then we're going to say, well, your confidence level for what? And if it's a mean, tell us, okay, mean. And then I'm going to say, well, your mean what? So then tell us what the variable is. Tell us what the population is. And then the interval itself with units if there are units. With a point estimate of, and if you're looking at means, this will be your sample mean with units. So for context, the zinc concentration river, the 95% confidence interval for the mean amount of zinc concentration in the river, so for all locations on this river, is estimated to be between at 2.502 grams per milliliter to 2.698, we rounded a little right there, grams per milliliter, with a point estimate of 2.6 grams per milliliter. So here I have my confidence level. I know that it's mean. Amount of zinc concentrations, the variable that we're collecting for all the locations. The population is going to be for all locations in this river. And then my actual interval, so 2.5 grams per milliliter, 2.7 grams per milliliter, then my point estimate with units. If it makes more sense to rearrange this sentence, so it'll make sense to you, we're cool with that. But just know that we pretty much have a checklist and we're going to look for all of these things. You definitely don't want to just mix the parts around without really thinking about if the sentence makes sense. But if it makes sense to rearrange it differently, then go ahead. We're totally fine with that. The template is just so that you hit all the things we're interested in having in that write-up. So this is the two-part write-up. Essentially, the two parts is, this is the first part, this is the second part. So if you see a two-part write-up template, this is what we're talking about. And yeah, we have it written up so it's all one sentence. You can write it up as two if you want. So confidence levels. You're going to see 90% confidence. You're going to see 95%, 99%. It's really uncommon to see any other confidence level. I mean, you might have that like random that comes up to you and go, oh, check out my 98% confidence. But you're like, okay, it's a little weird. It's very uncommon that anybody uses anything besides these three. And so things to know is the higher your confidence gets, the more likely, like, just based on, like, more of the intervals made this way will have that true parameter or true mean or whatever you're trying in there. But it makes it wider. So it's kind of, yes, it's more likely that that you randomly sampling and calculating a confidence interval has the actual mean in it, but it is wider. So, absolutely, it's a trade-off. You can have 100% confidence, but if you think about it, 100% confidence is usually so wide it's not useful. So I imagine somebody's like, well, I'm 100% sure that these average zinc concentration for all locations in this river are between 0 grams per milliliter and infinity grams per milliliter. It's not a useful interval, right? It's basically all possible values. It's not useful. So you really want to strike some sort of compromise. You don't want it to be so wide it isn't useful, but you want it to be wide enough that it probably has your parameter in it. So that's what this comparison is. For 90%, it's the most precise. What that means is it's the narrowest. So 90% is the narrowest. Which is nice for it to be narrow, but it's because it's narrowest, it's also more likely to miss more often. Okay, so it's more likely to miss more often. Then in contrast, the 99% confidence interval, it's the widest out of these three. It's the most likely, like when you're doing this process, to actually produce a confidence interval that actually has the true parameter or mean in it. However, it's less precise, so it's wider. Precise is narrow, less precise is wide. Folks would be a little miffed with me if I said, oh, well, I have a 90% confidence interval or 99% confidence interval for the average score on an exam out of 100. That the average is between 10 and 100. It is so wide that it's not useful. So it's not to say that all 99% confidence intervals are that wide, but it's worth noting, like, hey, if it's so wide it isn't useful, maybe look at having a lower confidence level. And then the compromise between the two. 95% confidence is probably the most commonly used out of the three. It's not, quite as narrow as the 90, but it's not so wide as the 99. It's 95% of the time you're making a confidence interval, it works correctly. So 95% is fairly good, but it will depend on how important it is to really to capture this this parameter. So this is just another image here where here it's showing, hey, here are 90% confidence intervals when we simulated from this population, and these dashed lines, they represent intervals where that interval doesn't intersect with the true value. So it means that it's, like in this case right here, this entire confidence interval is above the actual average. If you look here, this entire interval is actually below it. And if you look across all of the possible ones, roughly 10% of them are missing. They're either above or below that true mean. Versus if you look at 99% confidence, they are wider than the 90% confidence intervals, but they miss less often. So it's definitely worth keeping in mind. So considering all of this, which confidence level will be more precise? By more precise, we mean narrow. So I have never heard of anybody using a confidence level of 50%, but 50% will be the narrow. So, think if I had the middle, 50% here. Wow, that is definitely not 50. 50% here. This middle 50%. If I want an 80% confidence interval, it's 50% plus some, right? So 80 is 50 plus, so it's wider. So whatever the confidence level is, the smaller confidence level is narrower. The larger confidence level is wider. So hypothesis testing. So the flip side of confidence intervals is now saying, hey, yes or no statement. Can we say that the average OSU student height is higher than 62 inches or something like that? So here, maybe you want to test whether the average exam score is different than claimed. Claimed by who? I'm not sure. Test the proportion of students that cheated at a university. If that's higher than claimed, I don't really know how you would test that, to be honest. Compare the average response of two treatments. So you might want to say, like, hey, I have a new medication that reduces fever, and I want to compare it to whatever medication is already on the market. You would compare, the fever reduction between the two. So testing whether there's an association between two categorical variables or maybe two quantitative variables. So you want to know, hey, are these two things related to each other? Be careful. You don't want to say, does one cause the other, unless it's specifically like a randomized experiment. You want to be very cautious about that. So here, hypothesis test, you might also hear them called significance tests. It's a formal procedure, so we have all these steps like, oh, well, what's the question of interest? What's the parameter of interest? What are the hypotheses? And we have step by step that we go through. So anytime we mention these hypotheses, there's that null hypothesis and alternative hypothesis. They only have parameter values in them. So if you're looking at a population proportion, you're looking at P. If you're looking at a population mean, it's mu. If you're looking at the mean for two different populations, it's mu1 minus mu2. And you can change the 1 and 2 labels. Your hypotheses should never, ever, ever have anything from the sample. The idea is that you don't even have a sample collected when you write it. So if you are using sample information like or X bars or P hats in your hypotheses, that's not quite right. And so then we end up expressing our results here like, hey, if this, null or default statement is true, how weird is what we saw in our actual sample? Based on that, do we really think that the statement's true anymore? That kind of idea. So the hypotheses, null and alternative. So null, it's denoted by H not for like nothing, not like, I think they've been calling the 2000s the naughties. I don't know. I hope it doesn't get traction. It's kind of a weird, awkward name. That's a 0. And then the alternative, it's usually the claim we're interested in finding out. So the null is boring. It usually is the claim. Hey, we claim that the average height of all OSU students is 62 inches. The alternative would go, oh no, the average of all OSU students is higher than 62 inches. So there are a few different ways. So you can have HA. It doesn't matter if it's a uppercase A or a lowercase a. It makes no difference. If you look online too, you also might see H with a 1. Kind of goes with the 0. But it's a little confusing. So we have a tendency to use A, alternative hypothesis. And so in the end, we're going to collect evidence, and that evidence is supporting our alternative. And if it's strong enough evidence, we're going to say, hey, you know what? We don't believe the null anymore. Let's go with the alternative. If it's not strong enough, we're going to say, you know what? We don't have strong enough evidence to throw the null out. Be careful, though. It's not the same as saying we prove the null is true. We never prove the null or support the null. That's very much not what we're doing. We will jump on that every time. So the idea in the U.S. court system, supposedly, they're supposed to assume innocent until proven guilty. So like that's your default. It's the idea that innocent and your alternative is guilty. So if you have enough evidence, you'll throw this null out and conclude that they're guilty. That's the idea. And the idea, too, is you're the prosecutor. So you're only providing evidence against the null. You're never providing evidence for it. Super not your job. So some facts here. So here we're pretty much trying to figure out how strong the evidence is against the null. So against the null / for the alternative. They're pretty much the same in our mind. So if the stronger the evidence is that the null isn't true, you're pretty much demonstrating, hey, we actually think the alternative is true. And then typically, almost always, at least in this class, the null hypothesis almost always has an equal sign in it. Like null, if you're dealing with means, mu is equal to, I don't know, some number. It's going to be a stated number. But typically, the null is, we like to say the null is dull. It's whatever the claimed value is. It's equal to. We don't mess with other signs in the null hypothesis. And typically what we're interested in doing is rejecting the null and saying, hey, let's go with the alternative. We like the alternative now. We've gotten enough evidence that we don't believe the null anymore, so now we believe that the alternative has to be true. And that does mean that we have to set it up so only one can be true at a time. They can't really be overlapping. So one-sided versus two-sided. So one-sided hypotheses, it totally is going to matter the question of interest. If you're reading the question prompt and you can tell they really want to know if, the average is less than a value or if it's greater than a value. They only are interested in one direction in particular. So greater than, less than, exceeds, at least, at most. Two-sided, we want to know if they're different, but we don't necessarily, at least from the question prompt, have a suspicion. Okay, so you have to be able to write these without looking at what happened in the sample first. If they just want to say, hey, is there a difference in height between first year and second year OSU students? Well, we're pretty much just going to look to see, we don't know which one we think is taller, so we want to look in both directions. So it's two-sided. So different than, differs from, not equal to, other than. Oops, I do not know what my mic's doing. That kind of idea. So if you have a greater than sign, a less than sign, it's going to be one-sided. This is some generic, this is theta. It would be mu if you were looking at means. It would be p if you were looking at proportions. And then theta not, that it's just a stand-in for an actual number value, which you would put in there. You would actually plug in a number. And then alternative, not equal to, that tells me two-sided, because I need to check to make sure it's not higher, and I need to make sure it's not lower. So here is an example. Good place to pause and give this a try. We have a large bio class. Curved is a real... Trust me, when people say, will you curve this, they don't mean curve. Curving actually makes a bunch of people fail. So we have the exams are set up so the average score is 75. They are really unhappy with one of their TAs, and I guess they want to make a question out of it, which seems really mean. So students are randomly assigned to lab times, so we can basically assume that the students assigned to this TA were at random. So we can say anything that really any difference in their scores we could really blame on this TA, which seems really kind of crappy. But that's our question here. So what are the null and alternative hypotheses? So starting off, we're looking at exam scores. It makes sense to average them. So this is we're going to be looking at a mean. So we want mu specifically. We will go through all the way on that problem, but we're going to talk about what we're going to do while we get there. So we have the statement, so we make these hypotheses, and then we actually want to find, okay, well, if the null is true, how weird is what we actually saw in the actual sample? So we calculate a test statistic. And when we calculate a test statistic, we can use a z-table or a t-table or calculator and find, okay, well, here's a p-value. This is the probability that what we saw in the sample, so this or something more extreme from what the null is saying, would have happened if the null actually were true. So we're not going to compare to a rejection region. Let's compare to significance level, or significant, that the rejection region is a language from a different course. So in general, the test statistic, it's always going to be whatever you saw in the actual sample, so theta hat or point estimate minus whatever's claimed, divided by some sort of spread, so the standard deviation or the standard error of the estimate. So p-values. So the idea is, assuming the null is true, the probability that sample statistic would have had the value we saw in the actual sample or more extreme, so it totally depends on what your hypotheses say. The probability that we would have observed that or something more extreme. That's our p-value. So two-sided. I really don't like these pictures so much. I will draw a picture for the other one. But yeah, so this one was just asking, hey, is mu different than some number? This one was specifically asking, hey, is mu less than some number? That kind of idea. Probably the same number, actually. In general, if we're using the z-table or the t-table, we're calculating our one-sided p-value. If you want a two-sided p-value, all you have to do is multiply by 2. If you want a two-sided p-value. So making decisions, it's going to matter. You're going to have a significance level. This is decided ahead of time. It's pretty much saying, hey, if we have a p-value smaller than this value, we should basically say we don't believe the null anymore. It's basically this threshold. Hey, if our p-value is smaller than this, what we saw based on the null hypothesis, it doesn't match, we'll throw out the null. So we use this Greek letter alpha, and typically you have 0.10, 0.05, or 0.01. R.A. Fisher is some dude who just really, really liked 0.05 way back in the day. It's not necessarily that there's a scientific basis for it, it's just really popular. So keep in mind, it's kind of going to come down to some degree, like how bad a type 1 error is, and we'll go into type of errors. But know that if for any reason it doesn't state a significance level, 0.05 is a default if not stated. Here we go. So if our p-value is smaller than our significance level, we reject. If it's bigger than our significance level, we fail to reject. Small p-values make us happy, right? We like our p-values low. If the p-value is low, then the null has got to go. If you've seen that p-value song, that's from the p-value song. So small p-values, strong evidence. It means that what we actually saw in the sample is really unlikely to occur if the null is true. And we know that what happened wasn't that weird, so we don't believe the null anymore. If you have a really large p-value, it's saying, hey, if the null is true, then what we saw in the sample happens all the time. It's not really setting off any red flags. We're fine. So it's not conclusive. You don't get a reject. We also can talk about the strength. So it's very strong or moderate. Once again, the small p-values provide stronger evidence. Larger p-values, little to no. I don't like to say no evidence because it's not exactly that it's no evidence. It's just really, really weak. Around 0.05, it's moderate. So moderately strong, moderately weak, some. It's kind of a weird phrase there. But so the smaller your significance level is, the more extreme your test statistic has to be in order to reject. However, be careful. It's reject and fail to reject. You never accept the null. Don't do it. We will jump on it so fast because proving something, basically saying, hey, we don't have evidence that this is wrong. We didn't say we have evidence that it's correct. It's yeah, in English, most times double negatives would work that way. In stats, it really does not. We'll jump on it every time. So here, hypothesis testing for a mean. We're looking specifically at a z-test so we know what sigma is. So if we know the population standard deviation, so sigma, we can perform a one sample z-test. So we can go ahead, we can take our sample mean minus the claimed value over sigma over the square root of our sample size. We do have, pretty much most of the time, we'll have 3 conditions to do this z-test. We need to know that we used random sampling for our sample. We need to know that our sample size is big enough for the central limit theorem to kick in. And then we need to know the population standard deviation. If we don't, we have to go to T methods or T procedures. It just pretty much changes. Instead of a z-test statistic, it's a t-test statistic. So doing our hypothesis test in 4 steps. So the first is saying, okay, well, what's the question the researchers want to get at? And this is really important to keep in mind. Is this a yes or no question? Is this open-ended? Are we asking, hey, what is the average height of all OSU students? Or are we asking, hey, is the average height of all OSU students taller than 62 inches? That kind of thing. That kind of gives away, hey, if it's yes or no, hypothesis test. Open-ended confidence interval. So then identify the parameter of interest. If we're in a scenario where we're looking at a mean, it's going to be mu. But then we're going to want to probably put in words like mu is the mean, whatever the variable you're collecting, of whatever population you have. We're going to state our hypotheses as the null and alternative. We need to write down our significance level. If we provide it, use the one provided. If none is provided, use 0.05. So check those conditions. Hey, is it a random sample? Is our sample size big enough for a central limit theorem to kick in? Do we know sigma? Calculate a test statistic, get your p-value, and now you can actually write up your conclusion. So we have a 2-part conclusion for this as well. So using the results from the test, like 1, we're going to want to know if we reject or fail to reject the null. But then we want a translation, like, hey, let's put that in layperson speak. Like, let somebody who is not a statistician be able to read it. So similar to the confidence interval, here's a template for that. So 2 parts. This first part is telling us whether or not we reject it. It mentions our p-value and it says our significance level. And then this is a deceptively small blank. It's honestly probably a lot bigger. But there is, and then you talk about how strong the evidence is to suggest that. And then we have to basically write out what the alternative is, but in context of the problem. So there is very strong evidence that the mean zinc concentration for all locations on this river is, I don't know, higher than 2 grams per milliliter. I don't know, something like that. So we're back to this weird example with a biology class. The average exam score is 75. And so they go ahead and they randomly select essentially 36 students in that TA's lab. Those 36 students have an average of 69 on the exam, and the entire class is, I don't know, standard deviation is 12. So this is sigma, and this is x bar. This 75 is the average for the entire class, and then n is 36. So is there evidence that the students from the TA's lab will score lower than the entire class on average? Very, very important, the average part. So stating, we want to say, like, hey, what is our question here? So How about this? Is the average score of all of the TA's assistant students less than the class as a whole? So is it less than 75? Because we want that number in there. We want to know what we're comparing it to. It's not a lot of information if we don't put that number in. So the parameter, it's the average of all student exam scores that teaching assistant has. The symbol for it is mu. The hypotheses here. We're going to start off saying, okay, the average score of all of this TA students is 75. And the alternative is we're worried that they're lower. So mu less than 75. And our significance level, if you look back, I don't think it's specified in there. So we're going to use our default 0.05. So checking our conditions. So they randomly selected these students. So that's good. They want to know, hey, is our sample size large enough? We had 36. That should be. That should be big enough for the central limit theorem to kick in. And then, do we know the population standard deviation? Yes. Because in this scenario, we have the scores of all the students. So we do have sigma. So then calculating my test statistic, it is going to be a z test statistic because I know sigma. Sorry, yeah, z test statistic because I know sigma. So plugging in the claimed value, that's 75. Well, yeah. I end up getting a z test statistic of -3. What this means is for all possible unique samples of 36 students from all the students, these 36 students are three standard deviations below average. So this is telling me hey, this group of students is well below the average, for sure. And so this is a one-sided p-value, because if it's 75 as claimed, and we're looking at 69 or lower, this shaded area is our p-value, which you can use a z-table, you can use a calculator. We get a p-value of 0.0013. So this is saying, hey, if the average of all of these TA students is 75, like the rest of the class, the probability we would have randomly selected 36 of them and they would have had an average of 69 or lower, that would only happen 0.13% of the time. That would happen less than 1/2 of 1% of the time if this null were true, which is going to make me think, I don't think this null is true. It does appear that these grades are lower. So my two-part conclusion, first part, we're going to reject the null hypothesis with a p-value of 0.0013 at the 0.05 significance level. We absolutely need the second part. We need the translation, right? Because we're not all robots, and that's not how people usually speak. So we have very strong evidence that on average, the teaching assistant scores are lower than the class average of 75 points. And I do need to mention what the class average is. I don't want to just say it's less than the class average. We need to know what value we're comparing. So these are my two parts. I say that we reject it and why, and then I say, okay, well, there's blank evidence that our alternative is true, but in context. The context is the really important part. I would say it's probably worth a good chunk of the points there. So here are steps if you want to look at if you have a TI 83 or 4. Go ahead and check it out. I'm going to skip through it. So p-values and making decisions. So in general, if your p-value is less than your significance level, you reject, right? If it's greater than your significance level, you're going to fail to reject. So if you have a significance level of 0.05, if you have two different p-values, so you have a p-value of 0.0002 and 0.045, they're both smaller than 0.05. But, so I'm going to say p-value 2 and p-value 1. So this is my p-value 1, p-value 2. The red area here, that's 0.05 or smaller. So if our p-value is in that red area, it means, hey, we're going to reject. If you look p-value 2, it's like right at the edge. Like if it were just a little bit to the right, we would fail to reject. P-value 1 is way over, right? So we have much stronger evidence with that first p-value. So it makes a difference. You don't want to just say, oh, we have statistically significant difference. Well, okay, well, what does that mean? That's why we break out the, hey, no, there's very strong or convincing evidence versus there's significant. Significant just means it's smaller than your significance level. And the significance level is often fairly arbitrary. So confidence intervals versus significance tests, it totally matters, definitely like what your question is. But there's a relationship, especially if you're looking at a two-sided hypothesis test. So here, if you have a two-sided hypothesis test, let me see. Let's say I have a 90% confidence interval and a two-sided hypothesis test, 10. So if I reject my null, that means that, hey, whatever that claimed value is, not in 90% confidence interval. But if I fail, so FTR is failed to reject the null, that means my claimed value, I can spell some days, is in confidence interval. So things to note. So if you're looking at your confidence interval and the claimed values in it, and somebody's like, hey, is it different this? You're like, I don't know. It could be that claimed value. It's not saying that the claimed value is correct. It's saying it could be. Versus if that claimed value is outside of the interval, it's us saying, we don't think it is. That claimed value is not in my interval. I don't believe it's that value. So just know, hey, if it's not in the interval, we don't think it's that value. If it's in the interval, it could be. So no, it's not as definitive in that other direction. You're not like, oh yes, it definitely is this. It's more like, it could be. So type 1 and type 2 error. If you have me for 201, I think I have a somewhat fun example. I don't know. Depends. You might hate Star Trek. But whenever you perform a hypothesis test, you make a decision. So either you reject the null hypothesis or you fail to reject. Depending on what decision you make, you could be making a certain type of decision error. We call them type 1 error or type 2 error. There is no type 3 error. It's just one of these two. So the idea is it's kind of written funky. So this is the truth. This is reality. So if the null is actually true, but you reject the null, you've made a mistake because the null actually is true. You don't want to reject it. So if you reject it, it's possible you made a type 1 error. If the null is false and you reject the null, that's good. You wanted to do that. If the null isn't true, you don't want to keep it. Similar to here, if you have the null is true and you fail to reject, That's good, because if the null is true, you don't want to reject it, right? It's true. Type 2 error. So this is a scenario where the null is not true, but you fail to reject it. So you should have rejected it, but you didn't. So if you fail to reject, it's possible you made a type 2 error. And so it totally depends. If you make a decision where you reject, the only type of error you could have made was type 1. If you fail to reject, the only type of error you could have made is type 2. And it totally, it doesn't mean you made that type of error, it just means you could have. So just know there's a trade-off here. So we kind of set what our type 1 error is to begin with. That is our alpha, our significance level. But know that with type 1 and type 2 error, it's a trade-off. If you make type 1 error smaller, you make your type 2 error bigger. If you make your type 1 error bigger, you make your type 2 smaller. So it kind of is going to depend, like, if you look at the context, which one's worse? If you have one that's worse, you're going to want to make that one smaller. And it totally depends on the context of the problem. It's not like one is always worse. It totally it changes from situation to situation. So you can make your significance level alpha really, really small, but doing that, it's going to increase the chance that you make a type 2 error. So just know you can't always make them both small. The best shot you have at making both of them small is to have really large sample sizes. The larger the sample sizes, the smaller both of those errors go. But if you are just changing the significance level, it's going to be a trade-off with the type 2 error. So errors here, some fun visuals. We're not testing on those in particular. But know that probability of making type 1 error, so probability type 1 error, that's equal to our significance level. That's us saying we're willing to make this type of error this percent of the time, and it might need to be really small based on what the consequences of making that error is. For example, with the exam question, a type 1 error would have been concluding, yes, this TA's average scores are lower than 75. Well, maybe the consequence of concluding that when it isn't true, maybe they'd get fired or something. And that would be a really extreme consequence, right? Versus if they made type 2 error, it would mean the TA's students' scores are lower, but you didn't conclude that they're lower. So it really depends. Like, in the scenario, what's the worst scenario? And if it's really, really bad to make a type 1 error, makes your alpha smaller. So that is going to be the end of our week 1. This is just review. And so I look forward to talking with you all on the discussion boards. 99